The next thing we'll talk about are acid ionization expressions. An equilibrium constant can be used to determine how much hydrogen or hydronium ions will be produced when a weak acid reacts. We can also determine how many hydroxide ions will be produced when a weak base reacts. Looking at a generalized expression here, we have HA reacting with water to produce hydronium ions and A negative ions. This represents our acid, this represents our base, our conjugate acid, and conjugate base. When we write an acid ionization constant, what we do is we put the products over the reactants, and we make sure that they all are in aqueous solution. In this case, it's water, and that's a liquid. It's not included in our Ka expression. In order to determine the direction the equilibrium will favor, what we can do is compare the Ka of the acid with the Ka of the conjugate acid. If the weak acid has a higher Ka value than the conjugate acid in the same equation, the reaction will proceed in the forward direction and favor the products. If the weak acid has a lower Ka value than the conjugate acid, the reaction will proceed in the reverse direction and favor the reactants. Let's take a look at a couple of examples. In our first example, we have a reaction between sodium sulfite and acetic acid, and we're asked to write the Bronsted-Lowry equation, label conjugate acid and base pairs, and determine if the reactants or products are going to be favored. Finally, we'll write the Ka expression. The first thing that we'll do is look up sodium sulfite and acetic acid on our table so that we can get our chemical formulas, and we'll write a Bronsted-Lowry equation. Then we need to label the conjugate acid-base pairs. This is the acid, and this is the base, and here is our conjugate base and conjugate acid. Then what we need to do is take a look at our table and look at the Ka values for acetic acid as well as hydrogen sulfide ion. What we do is take those values right off the table, and we can write them underneath our chemical equation. We see that acetic acid has a Ka value of 1.8 times 10 to the negative 5, and hydrogen sulfide ion has a Ka value of 1.0 times 10 to the negative 2. Since 1.0 times 10 to the negative 2 is larger than 1.8 times 10 to the negative 5, we see that the reactants are going to be favored. Writing our Ka expression, we're going to take products over reactants, and this will be our Ka expression. In another example, we have a reaction between potassium hydrogen carbonate and lactic acid. What we're asked to do is the exact same things: write the Bronsted-Lowry equation, label the conjugate acid-base pairs, determine if the reactants or the products are favored, and write the Ka expression. So taking a look at our table, we'll get our chemical formulas directly from that table, and we'll label what the conjugate acid-base pairs are. There's our acid, there's our base, as well as our conjugate base and conjugate acid. Taking a look at our table, we can determine what the Ka values are. We see that for potassium hydrogen carbonate, we have a Ka value of 1.4 times 10 to the negative 4. And our carbonic acid, it has a Ka value of 4.5 times 10 to the negative 7. Since this Ka value is larger, we're going to see that the products are going to be favored. Writing our Ka expression, we take products over reactants, all are in aqueous state, and there's our Ka expression. That's everything for this video, and we'll see you on the next one.